Ciao, this is Luigi Boccia from the University of Calabria in South Italy. Within the framework of MTT-S Distinguished Microwave Lecture, I'll talk about the role of millimeter wave beamforming and integration technologies on non-terrestrial networks. In this presentation, we will explore how emerging technologies like millimeter wave beamforming and integration can shape the future of non-terrestrial networks, which are the networks that do not rely on traditional ground-based infrastructures. Let's jump into the talk by outlining the key topics we will be exploring today. First, we will establish the context by discussing how wireless connectivity is evolving. This is a very crucial point as it will provide a foundation for understanding the challenges and the opportunities that lie ahead. Next, we'll delve into system architectures, focusing on beamforming techniques and array configurations. Moving on, we will examine the key technologies at the different integration levels: board, package, chip. This will highlight how components are miniaturized and integrated for efficient operation. We will then explore both passive and active beamforming approaches to conclude with the identification of some of the key open challenges in this field. Modern telecommunication systems are not just part of our daily existence, they are the very scaffold upon which our society expands, accommodating an ever-growing suite of applications. We are transitioning from the vision where 5G new radio was just a vision to an era where anyone to anything, anytime, and anywhere is a society need. This transition is propelled by the use of millimeter wave technologies, which, despite their challenges of low output power and high link loss, are essential to enable enhanced mobile broadband for ultra-reliable low latency communications and also for machine-to-machine communications. In this context, the role of satellite communications radically changed. Where we had only GEO and some MEO satellites, and satellite communication was generally a bastion for broadcasting and defense, in the last few years, we have added two layers to these infrastructures. The first one being the aerial layer, which is populated by low altitude platforms and high altitude platforms. These platforms are integrated with an increasing number of low Earth orbit satellites, and altogether they form what is called a non-terrestrial network. How are we going to use NTN? Well, in this case, private companies are running faster than regulatory bodies, as we all know that there are already some LEO services being operated these days. There are manifold ways to use non-terrestrial networks. The first example is a user equipment which in near future will not be only linked to the ground segment, but it can be connected to a high altitude platform or directly to a LEO satellite. These links can be operated below 6 GHz. This is referred to as FR1 frequency band, or even at higher frequencies, which are being defined by regulatory bodies as FR2. Do you think this is a scenario far to happen? Well, have a look at latest news and you will see that this is something which is being translated into reality in these last few months. The second case we can see is when a GNB network node uses a LEO satellite as a backhauling node. In these cases, the frequencies to be used are higher and it can go up to E-band. This means that the technology we will need to support this massive usage of non-terrestrial network at millimeter wave frequencies should be really improved to allow containing costs, simplifying the architectures, and facing the physical issues which underpin this type of connectivity. Using millimeter wave frequencies to establish a link to an aerial platform or to a satellite is not an easy task, and things are made much more difficult if we think that these systems have to be low cost as never before. To orient ourselves towards the technical solutions which are demanded, let's start making some distinctions within this domain. On one side, we have the space segment, where thousands of satellites are required for each constellation, operating in the Ku or Ka frequencies. Each satellite should provide a multi-beam coverage at low cost. On the other hand, on ground, we have manifold applications, including those requiring high data rate and low data rates, as, for instance, sensors or machine-to-machine terminals. To make things easier, let's focus on user equipment. Based on the distinction we have made in the previous slide, we can identify requirements for two types of user terminals. For instance, in the case of high data rate terminals, the ones which we want to have on our roof or in our boat, we have to imagine a transmit power of 2 watts, an antenna gain of about 40 dBi, and a noise figure per element of 1.2 dB. On the other hand, if we take into account the user terminal, which could be needed for IoT or machine-to-machine communication, the ones which we could place along with a sensor, for instance, the requirements are much loose, and we can accept higher noise figure, much lower gain, and even linear polarization. We do have technical solutions for both cases. The difference here is made by the cost of the final terminal. In the first case, we should target a cost not higher than €200 or $200, whereas in the second case, the cost for the user equipment should be much lower. A microwave engineer has a versatile toolbox in his disposal to address the different technical requirements we have just seen. Let's explore these options. At the antenna level, there are several beamforming architectures which might be considered, such as analog, hybrid, or digital beamforming. Additionally, we have access to routing-based beamforming configurations, including battle matrices, Rodman lenses. Each choice leads to a different system architecture, presenting a variety of building blocks that must be seamlessly integrated into the final circuit design. Another critical decision involves the selection of the integration domain. The same building block can be integrated, in some cases, on chip, in the package, or in the printed circuit board. And the decision we take significantly influence the complexity and the cost of the final product. Indeed, the capability to contain costs and to implement complex millimeter wave circuits is basically related to the circuit density. To illustrate the impact of these choices, consider a simple vertical transition of a transmission line. In a complex user terminal, we might require many such elements. While one of these transitions can occupy approximately 1 millimeter square in a printed circuit board, opting for on-chip integration, for instance, allows much higher densities. In the upcoming slides, we will dive into various examples that demonstrate how these distinct options can be leveraged to create entirely different system architectures.